Okay, we're picking up with example 4 in this video. The goal of this example is that we're going to be estimating roots of a quadratic function. So this example says that we have to solve negative x squared plus 4x minus 1 equals 0 by graphing. If exact roots cannot be found, we need to state the consecutive integers between which the roots are located. Next slide. Okay, so what we're going to do first is we're going to make a table of values and graph the function. Again, these values, the way they found them is by doing the vertex first, negative b over 2a. The value that they came up with for that was 2. So then you went 1 unit on each side, 1 and 3, and 2 units on each side, 0 and 4. Found the y values that go with each x value. So the vertex is 2, 3. Notice again these points are matching. They both 2, and these points are matching. So here we have graphed the 5 points from the previous slide, and notice how the points right here where they touch on the x-axis, they're in between whole numbers. So notice here this is 0, 0, the origin. Over here is 1, and this point, this dot right here, is in between 0 and 1. Over here, so we have 1, 2, 3. This point here is between 3 and 4, just like it says right here. So obviously our answer then is that one of our solutions is between 0 and 1, and the other is between 3 and 4. It might be important for you to look at the fact that this dot is closer to the 0 than it is to 1. So for example, if you were to actually estimate the answer and you were to come up and you guessed like 0.9 or 0.8, those would be bad guesses. A good guess would be maybe like 0.1 or 0.2 or something that's obviously closer to 0 than it is to 1. And similarly over here, this point is closer to 4 than it is to 3. So a smarter choice would be 3.8, 3.9, something like that, rather than 3.1 or 3.2. So here's a problem for you guys to check on your own. Practice this skill out. The equation is x squared minus 4x plus 2 equals 0. And you want to find which consecutive integers their roots are going to be between. So pause the video, work the problem out. When you have your answer, come back and advance to the next slide. So the answer here is that there are going to be 2 roots. The first root will be between somewhere between 0 and 1, and the second root is somewhere between 3 and 4. Okay, example 5, what we're doing here in this example is we're going to solve the equation by using a table. So we have our equation x squared plus 5x minus 7 equals 0. Okay, so all of this is some fancy language to look at the graphing calculator. So I'm going to open up my graphing calculator on my computer. And when you're going through these problems, you're going to want to use the TI-83 calculator as you're working. So okay, so picking up, you can see that I've got the graphing calculator over here on the right side of my screen. What we're going to do first is go to y equals on our calculator and type in the equation x squared plus 5x minus 7. It says we need to use the table window to find where the sign of y1 changes. So to get to the table, we're going to, we need to change delta table to 0.1. The way you change your delta table is you go to second window. We need to go to delta table and do 0.1. And I'm going to start my table just at 0 because I'm not sure where exactly the value is going to change. So to go to the table window, you want to hit second and graph. So starting here, I can see that 0, the y value is negative 7, then negative 6, negative 5, etc. So I'm going to scroll down until I find a y value that's really close to 0. Okay, can you see right here, 1.1, the value is negative 0.29, and 1.2, the value is 0.44, so it changed sign from negative to positive. So you know somewhere between 1.1 and 1.2, the function had a 0. So then we know, it says over here, we need to replace the process with 0.01 and 0.001 to get a more accurate location of the 0. So we're going to go back to our delta table second window, change 0.1 to 0.01, and I knew that the 0 happened somewhere between 1.1 and 1.2, so I'm going to start from 1.1. And then I'm going to go back second graph and look at my table again. Okay, notice here, negative 0.29, negative 0.21, negative 0.14, negative 0.07. Negative 4e negative 4 means negative 0.0004. So this is negative, and notice up here we have positive 0.07. So now I can see that the change from negative to positive happens somewhere between 1.14 and 1.15. But they want me to go back and look at 0.001, so I'm going to go back second window, change my delta table to 0.001, and this time I'm starting my table from 1.14, which again was the last time the graph had a negative y value on the table. So back to the table now, second graph. And notice here, 1.14, it's negative. 1.141, it's positive. So I'm going to go with the 0 happens somewhere between 1.14 and 1.141. I think I'm just going to stick with 1.14 for my answer. That's about as accurate as you're going to need to be. Let's come over here and check out the next slide. Notice they have all of the things that I just went through. Pretty much same numbers. Notice how this screen matches this screen over here. Let me get my face out of the way. So they said one solution is approximately 1.140, just like what we said over here, 1.14. Okay, here's a problem for you guys to try on your own. It says to locate the second 0 from the same example. So if you think about this, remember that when I put this function in my calculator over here, x squared plus 5x minus 7, I just started from 0. And when I moved on my table, I noticed that I was getting pretty close to this value around 1.1. But there's going to be some other 0 on here. And so what I would suggest you do is that you go through and look at the negative side, because these are positive x values right here. Look for some negative x values and see where you can find, if you can find the 0 from this function. So pause the video, work through that, and then come back when you're ready to look at the answer. Okay, so the second 0 from that function was negative 6.140. All right, we have a real-world example here. This is about the Royal Gorge Bridge. The highest bridge in the United States is the Royal Gorge Bridge in Colorado. The deck of the bridge is 1,053 feet above the river below. Suppose a marble is dropped over the railing from a height of 3 feet above the bridge deck. How long will it take the marble to reach the surface of the water, assuming there is no air resistance? Use the formula h of t equals negative 16t squared plus h naught, where t is the time in seconds and h naught is the initial height above the water in feet. So we need to think about h naught as our initial height. The deck of the bridge is 1,053 feet above the river. That's your initial height. Almost, but you're dropping a marble from 3 feet above the bridge. So 1,053 plus the 3, that's going to be our actual initial height. There's the 1056. We need to find, oh yeah, h of t is 0. That's going to set that to, that's going to be when how long it takes the marble to hit the surface of the water. The height of the surface of the water is 0 because this is 1056 feet above the water. The height of the water is 0. So we need to solve this equation. What we're going to do is we're going to throw that function in our calculator, adjust our window so that the x-intercepts are visible. I know you'll probably be really sad about this, but I'm going to take my picture off the screen for a moment. Okay, so we're going to go to y equals, type in our function, negative 16, oops, make sure it says 16. You can't use t, you're just going to use x again, x squared plus 1056. And if I just go zoom 6, that takes me to the standard window. I can see part of my function is here. It probably goes down really low and then comes back up again. But I need to adjust my window so that I can see the x-intercepts. Actually, I can see them here, but I can't really tell the shape of the picture, so I'm going to go to my window. Notice I'm only going up to 10, but I know that the bridge is 1056. So I might want to change my y-min maybe to, I don't know, negative 1000. Well, my y-max, I don't need to go anywhere with that. Let me look at the graph and see how this changes now. Okay, if you see this, how it's slanted up, now I'm kind of thinking it's an upside down graph. And I probably should have thought that originally because it's negative 16. So instead of going down in my window to negative 1000, I'm going to leave that at negative 10. And I'm going to go up to 1100. The reason I'm going up to 1100 is just because I want to make sure that I can fit in this 1056. Okay, this is a much better picture. This right here, maximum, that is going to be the 1056. That's our maximum height. And so what we want to find are the x-intercepts. So one of them's here. That's going to be at a positive time. This answer over here will be at a negative time. Obviously, you can't drop something in negative time. So this over here, this 0, that's the one we care about. The way we're going to calculate that 0 is we're going to hit second, trace, which takes us to the calculate menu, and we're going to find the 0. So you want to click on number 2. It's going to ask you this question down here, left bound. You want to take your cursor and scroll. It's moving kind of slow. Basically, you just want to scroll until you're somewhere to the left of where you know it crosses the axis. Right now I know I'm somewhere to the left because I can see I'm above the axis. It's positive about 360. Hit enter. Then it's going to change to right bound. You want to scroll some more until the sign changes from it's positive right now. Notice the y value is positive. You want to scroll until it changes to a negative value. Getting pretty close. 10. All right, negative 45. Once you change signs, hit enter. For your guess, you don't have to do anything, just hit enter again. And it's going to tell us the 0 happened at 8.1240384. Okay, I'm back on the screen now. Let's advance to the next slide. Here's our window, here's our 0. So the positive 0 of the function is approximately 8. It should take about 8 seconds for the marble to reach the surface of the water.